So, we have talked in detail about the chemistry of water. The next topic to tackle in our look at water is the hydrologic cycle, also known as the water cycle. The hydrologic cycle describes the patterns of movement that water follows between different states and reservoirs on Earth. This includes the liquid water found on Earth's oceans, lakes, rivers, and aquifers, the solid water found in glaciers and ice caps, and finally the gaseous water vapor found in the atmosphere. Water is continuously cycling between these different states. And we're going to walk through the hydrological cycle and see how those transitions happen. Our starting entry point to the hydrologic cycle is going to be liquid water. Liquid water is found in many forms on the surface of the earth, and it is also found in the surface layers of soil. When that water transitions into a gaseous state of water vapor, this is known as evaporation. Evaporation takes place from the surface of oceans, lakes, and rivers, but it also occurs out of the top layer of soil. This evaporation is where water vapor in the atmosphere comes from. There is also one other source of atmospheric water vapor, and that is plants. Plants contain pores in their leaves called stomata that are used to draw in carbon dioxide gas and spit out oxygen gas. You can see a microscope image of one of these pores here. These stomata not only exchange gases that are involved in photosynthesis, but also serve as a portal of transport through which water evaporates out of the plant. This process of water evaporating out of the pores in plant leaves is called transpiration. Then there is also a term that we use to describe the combined evaporation of water via transpiration out of plants, as well as evaporation of water out of soil, and that term is evapotranspiration. So, evapotranspiration is an umbrella term that includes plant transpiration and evaporation, but does not include evaporation from the Earth's bodies of water. So, bottom line, there are several pathways by which liquid water gets released into the atmosphere as water vapor. Once there, the water vapor gets carried upward as it rises with the rest of the air. And as it rises higher in the atmosphere, it cools. The cooling of the water vapor causes it to undergo condensation, the process of a gas turning back into a liquid. As a result of condensation, droplets of water form in the atmosphere, and as those droplets accumulate, they will combine with others to form larger droplets until they become visible in the form of clouds. Eventually, when the droplets become large enough, they can no longer remain aloft in the atmosphere, and gravity pulls them down to Earth's surface. This phenomenon, called precipitation, the process of water falling from the clouds as rain, snow, sleet, or hail. So now the water has returned to the surface of the earth. What happens to it next? Well, some of that precipitation will flow deep into the ground. This process of deep water absorption is called infiltration. Water that infiltrates deep enough can become part of what's called groundwater. Underground bodies of water, also known as aquifers. Aquifers are what people are tapping into when they dig a well to source their water. The upper surface of the aquifer is called the water table. So, to be able to access groundwater, you have to dig deep enough to reach the water table. And before we carry on with our journey oops, through the water cycle, we need to take a moment and talk about the importance of aquifers, because aquifers represent a significant source of fresh water that is used for human consumption. About 30% of the liquid fresh water on Earth is stored in underground aquifers, and humans draw heavily from them for their water needs. However, aquifers are not as renewable of a resource as one might think. Aquifers are filled through precipitation that falls over a large area of land space known as the recharge area, and only a fraction of that precipitation infiltrates down into the aquifer. As a result, it can take hundreds to thousands of years for an aquifer to fill, especially in areas that receive little precipitation. Aquifers in the Sonoran Desert, for example, contain water that soaked in thousands of years ago. And now, a multi decade long drought in the Southwest has caused even lower precipitation rates that are further harming aquifer recharge. On top of that, humans in Arizona are drawing out groundwater at a rate much faster than is being replenished. So fast that water experts are in the state consider much of the water unrecoverable or unlikely to ever be replenished. A common way that the volume of water in an aquifer is measured is by looking at well digging data to assess how far the water table has dropped. So how does the well how deep does the well have to be dug to access the water table? Many wells in Arizona have existed for many decades. And so we know that groundwater levels are dropping as people have to go deeper to access the water table. This figure shows number of feet that the water table has dropped in various regions of the state of Arizona since the year 1950. You can see the scale ranges from 0 feet dropped all the way up to over 160 feet. At the high range, that's about the height of a 16-story building. Water levels in 25% of Arizona wells have dropped by more than 100 feet since they were drilled, and nearly half of wells have dropped more than 50 feet. The most severe drops are taking place in rural areas where there are no laws regulating how much can be pumped. For example, in the agricultural basin around the city of Maricopa, the water table has dropped 125 feet since the 1950s. Needless to say, overdrawing our aquifers is a serious threat to water resource in our state. We'll talk more about this later, but right now let's get back to the water cycle. Okay, so we know that some precipitation water infiltrates the ground and becomes part of groundwater stores. But eventually soils may become saturated with water from a precipitation event and no more water can infiltrate. At this point, overland flow will take place. Overland flow is also known as surface runoff. It's the movement of precipitation water over the surface of the ground, where it gets carried into streams, rivers, or other mobile or stationary bodies of water. Once it's part of a river system, the movement of the water is referred to as stream flow. Eventually, stream flow carries the water back to the ocean. We refer to the geographic area that is drained by the stream flow of a particular river system, a drainage basin. And for perspective, once it's part of a river system, uh, this illustration shows the drainage basin of the Colorado River, which covers the path of the Green River as far north as Wyoming, which meets with the Colorado in Utah, and then travels south into Arizona along the borders of Arizona and California, and then eventually drains into the ocean and the Gulf of California between the states of Baja California and Sonora in Mexico. A few final details we need to talk about in the hydrologic cycle are underground discharge and glaciers. Groundwater is not only removed from aquifers by humans, it can also seep upward through a spring. This process is called groundwater discharge, also known as seepage. And then finally, we can't close out the water cycle without addressing solid water as well. Glaciers and ice caps are the largest reservoir of fresh water on Earth. About 69% of the planet's fresh water is found in ice. They are not commonly used as a direct water source because they tend to be remote, far away from human settlement, and of course they are solid, not liquid. But the huge amount of water they store means that changes in Earth's climate conditions can have significant consequences for the state of water on Earth. During the last ice age, up to 50% more water was stored in the form of glaciers than it is today, because more water was tied up as ice is less in and as less in liquid form. Sea levels at the time were about 100 meters, approximately 300 feet, lower than they are today. In addition, a jump in sea level has been observed over the past century as the earth warms and ice caps and glaciers melt. This figure here shows the increase in sea level since the year 1880, based on two separate measurements that track very closely with each other, tide levels and satellite measurements. As you can see, sea levels have has risen nearly 10 inches since 1880 and is on track to rise further as the global climate continues to warm. Now, in our next section, we're going to talk about human water usage. But before we do, we need to lay down some basic information about the availability of fresh water on Earth and terminology referring to the different types of freshwater sources and methods of water use. Out of all of the water on Earth, 97% is saline, meaning salt water, and only 3% is fresh water. Saline water is useless for most human enterprises because of its high salt content. So, when we're looking at water as a resource for human consumption, we're really only looking at the 3% that is fresh. Of that 3%, about 69% is found in ice caps and glaciers. As we said, about 30% is stored in underground aquifers, and only about 1% exists as a liquid in a surface source like a river or a lake. Of that 1% of liquid, surface freshwater, about 87% is stored in lakes, 11% is found in swamps, and 2% is found in rivers. So, overall, the message here is that freshwater is a rare and precious resource, and it's that humans rely on for many, many things. Before we talk about the different sectors of human water use, though, let's establish the different categories of usable water. When we talk about usable water, there are four different categories that water managers have created into which it can all be divided. Blue water is the term used to describe fresh water that comes from sources like rivers, lakes, and aquifers. Blue water is the most readily available and easily accessible, but because of this, it is also the most stressed water source because it's being overdrawn. Green water is rainwater that is stored in the soil and used by plants for growth. It's used to sustain ecosystems and agriculture. Although here in Arizona, our agriculture isn't really sustained by green water, it's sustained by blue water. Gray water is wastewater coming from domestic sources that is not contaminated with fecal matter. So this can include water that comes from dishes, laundry, bathing, etc. Gray water can be readily used for landscaping and irrigation of non-food crops, but in order to be used for human consumption, it has to be treated. Then finally, there's black water. Black water is wastewater that comes from toilets, so it's contaminated with urine and feces. This water is considered a biohazard and has to be heavily treated before it can cycle back into use for any purpose, including agriculture. So, those are the four categories of usable water. And to give you some idea of how our state's water resources are distributed across these categories, this chart does not include green water, which remember is rainwater, which in many parts of the state is a very small amount. But among the other categories of usable water, 36% of our water is sourced from Colorado River, brought down from the northern part of the state in canals. 18% is sourced from in-state rivers like the Salt River and the Verde River, and 41% is groundwater that comes from aquifers. All three of these are blue water sources. The remaining 5% is reclaimed water. So this is gray and black water sources combined and labeled reclaimed water. So as you can see, in Arizona, the overwhelming majority of water is blue water, the most strained category of usable water. Now that we understand the different categories of usable water, let's look at the different sectors that use that water. There are six main sectors. The first of which is the industrial sector. This sector uses water in manufacturing processes. The agricultural sector uses water for growing crops. The domestic sector uses it for household purposes, which includes landscaping. The livestock sector uses fresh water to supply to livestock and also uses it for aquaculture or fish farm operations. The mining sector uses water to mine ore, coal, and other fossil fuels. And finally, the thermoelectric power sector uses water in the generation of electricity. How much water is used by each of these sectors varies widely from place to place. But to give you an idea of how the pie is sliced in our state, here is a figure showing the breakdown of Arizona's freshwater withdrawals by sector. Now, this does not include green, gray, or black water. This only looks at how the blue water is being used. As you can see, almost 76% of blue water goes to agriculture. A little over 20% goes to domestic and municipal use. And then the other sectors consume very small amounts. These four sectors add up to about 4% altogether. In our next section, we will be looking at water consumption patterns in the country as a whole and how they are distributed across these sectors. But just a few more terms to define before we get there. Human water can either be consumptive or non-consumptive. Non-consumptive use is when water is removed from a source and then returned right back to that source after it has served its purpose. An example of non-consumptive use could be the use of water to cool a nuclear reactor. The photo that you see here is of 3 Mile Island, the notorious nuclear generating station that underwent a partial meltdown and almost caused catastrophe in 1979. It's now been decommissioned, but it's called 3 Mile Island because it's located on an island in the middle of the Susquehanna River in Pennsylvania. And in terms of water use, the middle of a river is a great place for a nuclear power plant because nuclear power plants use a lot of water for cooling nuclear reactors. So they can withdraw that water from the river, use that water for cooling, and then reroute that water right back into the river, and that's considered non consumptive use. Consumptive use, on the other hand, is when water is removed from a source and then not returned, it's fully used up. An example of consumptive use is withdrawing water to supply to livestock. The livestock drink the water, it becomes part of their bodies and their physiology, and it does not get put back into the aquifer or lake or river from which it was drawn. Another term in the realm of water consumption is withdrawal. Withdrawal is the total amount of water removed from sources, including both consumptive and non-consumptive uses. And then finally, return flow, which is the amount of water that gets removed from a source but later returned. So the water that is dedicated to non-consumptive use. So keep these terms in mind because as I mentioned in the next section, we will be getting into more detail about what water usage looks like in our country and in our state.